Welcome. Today we finish up Unit 12, Logarithmic Functions. We are in Day 3 and we look at logarithmic and exponential equations. This is 6.6 from the book and we will look at objectives 1 and 2, basically solving logarithmic equations and solving exponential equations. Here's the big idea. There's two basic forms of equations for logarithmic equations and for exponential equations. Basically with logs, if log base a of m is log base a of n, then m equals n. For example, if log base 5 of x equals log base 5 of 13, then I get simply x equals 13. And there's a very simple version with exponential equations. If a to the m equals a to the n, m equals n. So if I have to solve 10 to the x plus 2 equals 10 to the 7, then I get right away x plus 2 equals 7, or x equals 5. Of course, these things have variations that become more interesting. In the log side, if log base a of m equals b, just some other number, then by the definition of logs, this tells me that m is a to the b. For example, if log base 2 of x squared is 6, then I know that x squared is really 2 to the 6. Now 2 to the 6, it turns out that's 64. And so look at that, 64 is a perfect square, x squared equals 64, so my solutions are x equals plus or minus 8. And there are variations, of course, on the exponential side. If I have something like a to the m equals just some number b, there's a trick that is often very helpful. What we do is we take the natural log of both sides. Natural log of a to the m equals natural log of b. And at first it might seem weird. Why do we do this? Well, let me show you. I'll give you an example. Suppose I want to solve that 2 to the x equals 23. Then the natural log of 2 to the x is the natural log of 23. And now, here's where I can use my property of logs that that exponent on the inside comes out in front. So this is x times the natural log of 2 equals the natural log of 23. And now I can solve for x. Just divide both sides by ln 2. And there's our answer. All right, in the rest of this video, I'll go through a bunch of examples. I'll do a bunch of different logarithmic equations and some exponential equations. Every time there's a new page of problems, please use active viewing. Pause the video, give it your best try, think about these things before you see me go through them. All right, let's get started. Starting simple, how about log base 3 of 5x equals 2? This tells me 5x equals 3 squared. Of course, 3 squared is 9. Divide both sides by 5, x equals 9/5. In the next problem, it's a natural log, but it's the same idea because natural log is log base e. So I can say x plus 4 equals e to the 8 power. And subtract 4 from both sides, x equals e to the 8 minus 4. As an exact answer, this is as simple as I can make it. But you can certainly plug this into your calculator to get a numerical approximation. All right, what if I have logs on both sides? In a way that really makes it easier. Log base 5 of x squared equals log base 5 of 9. The arguments are simply the same. So x squared equals 9, which tells me that x equals plus or minus 3. Now, it's very often the case with log problems, we need to be careful about what I put into the log. This first part, log base 5 of x squared, that x squared can't be 0. Whatever is inside of the log can't be 0. So I do know right away that x is not allowed to be 0. But that's okay. For my solutions, I see x is plus or minus 3, so that works. All right, number 4. Let's solve this thing. Natural log of x plus 4 is natural log of 12. So this tells me x plus 4 equals 12. And solving for x equals 8. And just to be sure, if I plug in 8 for x, is that okay? It is, because it just turns that argument into 12. How about absolute values? Sometimes you see these mixed around in log problems. But don't worry, it's really nothing more than what we've seen already. This first expression, log base 3 of absolute value of x equals 4, that just turns into absolute value of x equals 3 to the 4, which is 81. And so now I can use what I know about solving absolute values. This tells me that x equals 81 or x equals negative 81. And those are my solutions. Problem number 6. Let's see here. Maybe notice I have natural log on both sides, so I can really just compare the arguments. On the left, the argument is absolute value of x minus 3. On the right, the argument is 7. So those are equal to each other. And that tells me that x minus 3 equals 7, or x minus 3 equals negative 7. In the first case, adding 3 to both sides, I get x equals 10. In the second case, adding 3 to both sides, x equals negative 4. So there we go. My solution is x equals 10 or x equals negative 4. I want to show two more logarithmic equations. These ones are a little bit more involved, and they definitely use properties of logs. And I also have to be a little bit careful about what are my allowable x's. So let's go ahead and solve this thing through, and then at the end I'll double check my answers and I'll see if there are any extraneous solutions. Let's begin. One of the properties of logs is that if I add together two logs, that's the same as taking the log of their product. So this becomes log base 5 of the product x plus 6 times x plus 2. And on the right-hand side, I still have 1. Now let's use the previous solution technique where I say this argument, x plus 6 times x plus 2, that is 5 raised to the first power. I'll expand the left-hand side, x squared plus 8x plus 12, that equals 5. And we'll subtract 5 from both sides, x squared plus 8x plus 7 equals 0. So now I have a quadratic expression, and I can factor this guy. So this becomes x plus 7 times x plus 1 equals 0. And so now I know that x equals negative 7 or x equals negative 1. And it appears as though those are my two solutions, but here's where I need to double check and say which of those solutions can actually work in the logs. So let me take a quick check, and let's identify the allowable x's. In the first log, I know that x plus 6 has to be greater than 0. X plus 6 greater than 0. So this tells me that x is greater than negative 6. In the second log expression, x plus 2 is the argument, so I know that x plus 2 must be greater than 0. So in other words, x is greater than negative 2. And if I put these two together, x is greater than negative 6, x is greater than negative 2, I find that any solution I have has to satisfy that x is greater than negative 2. So looking back at my solutions here, negative 7, negative 1, only the negative 1 works, and the x equals negative 7 does not work. All right, let's try another. So in this problem, I have logs on both sides of the equation, and one thing that makes it difficult is that I can't just set their arguments equal to each other because I also have this factor of 1/2 in front. By a property of logs, if there's a constant out front, it can come and become the exponent. Now 1/2 is a little hard to work with, but here's a trick. Let's multiply both sides by 2, and so I get natural log of negative 2x equals 2 times the natural log of x plus 4. And now this 2 becomes a nice exponent that I can bring inside. So I get the natural log of negative 2x equals the natural log, I'll be careful here, the whole x plus 4, that gets squared on the inside. So now I can set my two arguments equal to each other. Negative 2x equals x plus 4 squared. Let me expand the square. And then I'll add 2x to both sides. And then hopefully this thing factors, and yes it does. This problem was cooked up so that it would factor nicely. So it looks like maybe my solutions are x equals negative 2 or x equals negative 8. Let's check for extraneous solutions. In the first log, negative 2x has to be strictly greater than 0. So negative 2x greater than 0, which tells me I could divide both sides by negative 2, and when you divide by a negative, it reverses the direction of the inequality. X is less than 0. All right. From the second log, I know that x plus 4 is strictly greater than 0, which tells me that x is greater than negative 4. On the number line, really what I'm finding is I have 0 and negative 4, and my x values have to be in that interval strictly between negative 4 and 0. So looking back at my solutions, I see that only one of them works, x equals negative 2, and the other guy, the negative 8, that was an extraneous solution. Doesn't work. Moving on to exponential functions. Solve 2 to the x equals 5. So as I said before, a good trick for solving these kinds of problems is to use natural logs. Just take the natural log of both sides. So ln of 2 to the x equals ln of 5. And now the x can come out front. I get x times the natural log of 2 equals ln 5. And now solving for x, I find x equals the natural log of 5 divided by ln of 2. There you go. This one is a bit more challenging. There's definitely some more arithmetic in this one, but the idea begins the same way. My variable is locked up in the exponents, and I want to somehow bring those exponents down. That's exactly what the natural log is great for. Whenever your variable is in the exponent, take the natural log of it and see what happens. Okay, here we go. I'll take the natural log of both sides. So by a property of logs, I can bring those exponents down. Now be careful when you bring it down to keep it in parentheses, because that entire exponent, x minus 2, that's being multiplied times the natural log of 5. All right, at this point, we need to solve for x. So here's our strategy. I'm going to expand both sides, so I'll distribute my natural log of 5 and distribute the natural log of 3. Then every term that has an x, I'll move to the left side of the equation. Every term that does not have an x will move to the right side. That will let us factor an x out of the left side and solve for x. All right, I encourage you to give it a try if you'd like. Otherwise, here we go. I'll show you what I can do. First, let's distribute both sides. Now, terms with the x, I'll move to the left, and this term that does not have an x, I'll move that to the right. On the left-hand side, now I have a factor of x, so I can factor the x out. And now I can divide both sides by the quantity in parentheses to solve for x. Now at this point we really are done. We've solved the problem for x. But what often happens in log problems is that there are equivalent ways of expressing the answer. For example, look at this top, the numerator of the fraction. That could be written as 2, and I factor out the 2, so ln of 5 plus ln 3, but natural log of 5 plus natural log of 3, I can use a property of logs, and that's really the same thing as the natural log of 15. So I could write this as 2 times ln 15. And that denominator, ln 5 minus 3 ln 3, well, that 3 out in front could become an exponent, so that could be written as ln 5 minus ln of 3 cubed. 3 cubed is 27, so then I get the natural log of 5 over 27, if you want. So I could write this answer as twice ln of 15, all divided by the natural log of 5/27. So, like I said, the answer that we got at the beginning is perfectly acceptable, but it is curious to see the different forms that answers can take when natural logs, or when logs are involved. All right, last idea, solving an expression in quadratic form. Here's an exponential equation. I have a to the x, a to the 2x. The variable x is in the exponent, so this is an exponential equation. And using some of our past techniques, this is very difficult. But, and you kind of need a little bit of a hint on this, if you know that this expression is in quadratic form, then it's easier to solve. Now recall, a quadratic, that's something like ax squared plus bx plus c equals 0. And you can solve this hopefully by factoring, or you can always at least use the quadratic formula to figure out what x is. So does this guy on the left have quadratic form? Well, 8 to the 2x, well, that's the same thing as 8 to the x being squared. And then I subtract off 8 to the x. And then if I move the 12 over to the left, I get minus 12 equals 0. And so this kind of has the form x squared minus x minus 12 equals 0. So if I can solve this and figure out what x is, then I should be able to solve the original one and figure out what 8 to the x is. So let's give this a try. X squared minus x minus 12 equals 0. This does factor. I get x minus 4 times x plus 3 equals 0. So x equals 4, or x equals negative 3. So this tells me that in my original expression, I must have that 8 to the x equals 4, or 8 to the x equals negative 3. Well, let's keep going. We'll solve for x. So on the left, I have the natural log of 8 to the x equals ln 4, or the natural log of 8 to the x equals ln of negative 3. And right away I see something bad here. No. Why is this a problem? Because there's a negative 3 as the argument of natural log. Natural log can't take negative 3. Natural log can be applied only to numbers that are positive. So continuing on the left, it looks like I have x times the natural log of 8 equals ln of 4. And so I get as my solution, this implies x equals ln 4 divided by ln 8. All right, and so there it is. We've finished the material there. We've seen a lot of different logarithmic equations and some different exponential equations and a variety of ways to solve them.